Hello, everyone. Welcome to our presentation about flame fractals. I'm Terian. Today, I'll be presenting with my teammates Christian and Drew, and we'll be diving into what they are, discussing how to make them, and some of the math behind them. So a little background to start off about fractals in general. All fractals share similar properties such as having self-similar shapes, a never-ending pattern, and a simple and recursive definition. There are many types of fractals, and we just wanted to highlight a few interesting ones, such as the Mandelbrot set, which is a famous fractal distinguished by its unique shape and simplicity, which is the fractal with the blue background up there in the picture, and also iterated function systems, which are repeated geometric shapes like the triangle fractal and flame fractals. And these are what we are studying today, which are actually a variant of iterated function systems, but iterated with nonlinear functions and affine transformations, which are transformations that preserve lines and parallelism, but not angles or distance. And fractals are interesting because they appear in everyday life. And to a careful observer, they can be seen in lightning, shells, or ice crystals. And they're also utilized for special effects in movies such as Star Wars and The Hobbit. Furthermore, they have applications in computer graphics, such as simulating landscapes or environments organically. Some of the math behind the fractals involve generating repeating shapes by using transformations. And flame fractals specifically use transformations such as scaling, projections, and rotations that are iterated through to shift a given point. And each function that is chosen has its own limit as it tends to infinity. And as such, some fractals can converge or diverge based on the limits of these functions. And later, we will also dive deeper into how eigenvalues play a factor in this.
All right, so the steps to actually generating a flame fractal are pretty simple. So the first step is you want to choose a point in R3, and we'll call this P, but normally we just refer to this as 1/2, 1/2, 1/2, because it doesn't really matter too much. And then you'll have a bunch of functions that you'll choose to create the fractal. So for example, you could have a linear, sinusoidal, and spherical like that. So the linear could scale certain points, sinusoidal and spherical could rotate in certain ways. So basically every iteration, you'll choose one of these random functions to apply to the previous point, and that will create a new dot on the 3D space. So you'll just keep doing this 50 million times, and then eventually you'll get this 3D cloud where at the end, to actually see it on a 2D screen, you'll have to perform R3 to R2 projection on the XY plane. Right, so here is one of our first fractals. We will refer to it as an ear fractal because maybe you can see it as an ear fractal if you want, but the next slide we'll go over how we actually created this. So again, we just started with a point 1/2, 1/2, 1/2, and then our equations of choice for the functions were the midpoint, spherical, swirl, and linear. So again, linear can scale it, while the swirl and spherical will make these nice curves and swirls as you see in the top right. Then the midpoint can also make more straight lines on the fractal. So after doing that 50 million times, we end up with a 3D space, and then we project it, and then you get this sense of depth in the fractal, as you can see.
So the next thing that we investigated came from just doing a lot of experiments with our program. We found that in some cases, the fractals would just not show up on the screen at all, and that depended on what we chose our linear transformation to be, basically what we put into the functions. This ninja star fractal is an example of a simple fractal that we created that was successfully rendered to the screen. So delving a bit deeper, we'll start by analyzing this ninja star fractal. As we went over, the first step for generating a point on the fractal is applying this linear transformation of the previous points. And we do that with this matrix. Assuming that there are no other functions that are applied, we can determine actually the end state behavior after applying this linear transformation over and over and over again, millions of times. We start by calculating the eigenvalues and eigenvectors of this matrix. Then we figure out a linear combination of these eigenvectors that can represent the initial state of 0.5, 0.5, 0.5, and that's what we're doing here. Using what we learned in class, We can now represent the state after applying n transformations using the eigenvalues, eigenvectors, and linear combination coefficients. By taking the limit as this n becomes really large, we find that the end state is actually the 0 vector. So what does this tell us? This tells us that the identity function approaches 0 for this fractal. Other functions, however, are chosen randomly and applied to x nu, y nu, and z nu, which may have alternative or even cyclic behaviors. What we've found is that for a good number of our fractals, the end state of this identity function heavily influences whether or not the fractal maintains in the screen view. So as an alternative, when the values were chosen that made the eigenvalues greater than 1, the end states of x nu, y nu, or z nu actually tended to infinity more often than not. And this is because the limit of this a to the power of n equation as n approaches infinity would actually become infinity as one of these eigenvalues is greater than 1. So for the exact same ninja star fractal, just with different eigenvalues, we get a nearly blank screen with just a couple points on it. And this is because the points are getting so big so fast that they can't even be rendered to the screen anymore. So in conclusion, we have a couple future recommendations of things that we would do if we had more time. And that would include adding colors to our fractals, basically giving each function a different color so you can see what role it's playing exactly in the flame fractal. And then also just experimenting with different fractal variants. But overall, our findings were that we can use linear algebra to predict some of the flame fractal shapes and their end state behaviors, and also that we can achieve some sort of a depth by projecting points in R3 to R2, which is on the screen. And this is just a gallery of some of the different fractals that we made using our program, and we gave them all names. And it really shows the different variety that we can use by using different functions and different affine transformations. So thank you so much for your time, and these are our resources.